Let's do another problem involving polytropic processes and a piston cylinder. In this case, let's solve a problem with the where the value of n in the polytropic expression is equal to 1. Air is compressed slowly in a piston cylinder assembly from the initial state where P1 is equal to 1.4 bar and V1 is equal to 4.25 cubic meters to a final state where P2 is 6.8 bar. Now, during the process, the relationship between pressure and volume follows the expression PV equals constant. You'll recognize that for a polytropic process, we have PV to the n power is constant. So obviously, in this case, n is equal to 1. For the air is the closed system, determine the work in kilojoules. So we'll lay out this problem first with a schematic. We've got air in a piston cylinder. Our system boundary is around the air only, which means our system is just the air and not the cylinder or the piston. Positive heat transfer into the system is indicated as a positive, energy going in is considered positive. Work done by the system, in other words, if the air were to expand and push the piston outward, then that would be considered positive work. But this is a compression problem because we're increasing the pressure of the air. And so we expect to get work done will be negative. Make a table of the given data. We know that the pressure in the volume of state 1, we only know the pressure at state 2, not the volume. And we know that the process relationship is PV equals constant. The next step will be to draw a property diagram. I'm going to draw a PV diagram. Let's plot state 1. We can see that it's at a pressure of 1.4 bar, that it has a volume of 4.25 cubic meters. And then the process is PV equals constant. That is going to end up as a concave line with increasing pressure. And it goes to state 2, which has a pressure of 6.8 bar, and a volume of V2. This is an unknown value right now. We're going to need to find that. We make an engineering model, a list of our assumptions. We're dealing with a closed system, so no mass enters or leaves. We're assuming that there's no change in kinetic or potential energy during the process. And we know we're dealing with a polytropic process that has a value of n equals 1. And we want to find the work in kilojoules. So let's start with the equation for a polytropic process that PV to the n power, in this case n equals 1, or PV is equal to constant. We conclude from that P1 V1 is equal to P2 V2. And we can solve for V2. It's simply P1 over P2 times V1. Now we can put the values in. P1 is 1.4 bar, P2 is 6.8 bar, and V1 is 4.25 cubic meters. So this gives us a volume at state 2 of 0.875 cubic meters. All right, the work from state 1 to 2 is the integral of P to V from V1 to V2. And we don't have to do integral calculus to solve this problem. We've already done that in a previous lesson. We can simply take the algebraic solution of that integral, which we know is P1 V1 times the natural log of V2 over V1, and substitute our values. We know P1 is 1.4 bar, V1 is 4.25 cubic meters, and we take the natural log of V2, 0.875 cubic meters, divided by 4.25 cubic meters, which was V1. And then we use our handy unit conversion that 100 bar cubic meters is equivalent to 100 kilojoules. Solving, we get the work for process 1, 2 is minus 940.4 kilojoules. Negative meaning that work has to be done on the system, which is what we expected to find because we are compressing the air, and the system, it takes work going into the system to do that.